Public Schools in New Delhi, India. Their innovation, called MagGlyde, is the autonomous magnetic takeoff and landing system. Please welcome Pectora.
It was Alan Kay who said that the best way to predict the future is to create it. And that's what we're here to do today. Namaste, ladies and gentlemen. We are Team Pectora. I am Raghav.
I'm Sarthak.
I'm Aman.
I'm Vedansh.
And I'm Yash.
So let's dive into. So as per available stats, nearly 61% of the total accidents occur during takeoff and landing.
And 50% of the fatalities occur during the same.
As you can see, the US Bangla airline 211 claimed 52 lives and Air India IX812 took a toll of 158 fatalities.
TAM Airlines Flight 3054 led to 199 fatalities, and Air France Flight 358 caused 43 injuries. So to solve these problems, here we introduce our product, MagGlyde, an autonomous system guiding and aiding the aircraft to take off and land perfectly. It performs regardless of weather conditions or the conditions of the runway.
MagGlyde leads to zero impact cushion touchdowns. Takeoff and landing will now be quicker and, more importantly, safer. So why do we need MagGlyde? MagGlyde counters these problems more effectively. Poor visibility, heavy crosswinds which deviate the flight path, slippery and short runways, excessive rainfall, inaccurate estimations by pilots, which are the leading cause of accidents in the aviation industry, and heavy snowfall.
So here we have the three main components of MagGlyde: the pad units, the ranging and tracking mechanisms, and the control systems.
The pad units are the basic or fundamental units of MagGlyde. Each pad unit can have many strobes. The strobes actually are bitter electromagnets. And these pad units will be deployed in the runway and their counterparts in the belly of the aircraft. All of these strobes will be individually controlled as per the commands from control block. And they can provide small correctional nudges and large push and pull.
So here's a picture for that. So this is a closer view into what's inside the electromagnet.
This is one pad unit, and all of these are strobes in there.
So, and here's a closer look at a 3D mesh of the entire thing.
Ranging. The basic idea of ranging is identifying where the airplane is. And what we mean by path traversal mapping is that we have already mapped how the airplane is going to move. And we're going to accomplish this by using short microwave pulses, because we don't want to get interfered with the engine sounds. And we're doing this in real time to avoid any time lag. And all of this will be done as per the control of the controller blocks.
So the true automation of the entire system lies in the intricate workings of the control system. The control system continually receives inputs from the OCS. It makes use of NASA Goddard's technology. The algorithm that we use is a chunking algorithm, which is analogous to the one that is used in data deduplication. So what this basically does is that it divides the pad units into certain zones, and each zone is given a unique hash identifier. And this data is all remembered and is used in later approaches to decrease the response time of the entire system. The decisions based on the algorithm are made, and the instructions to the pad units are given. And in turn, the magnetic orchestrations begin.
Now let me take you through the process of steps. First, ground control system establishes contact with the aircraft's onboard control system, exchanges the parameter and stats. Then a common approach plan is made. The onboard control system uses chunking algorithm to differentiate the pad units into zones, and magnetic orchestrations begin. The pad unit get activated, leading to zero impact cushion touchdown.
Rangers will set inputs to the control block, which in turn activates zones in the pad units, will lead to magnetic field modulation and a precise approach.
So here's a video of the takeoff with our system. So you can see the forces that are coming into action, and they're facilitating the aircraft to levitate further. And this is a similar video of the plane landing.
This shows that we can accomplish a cushioned zero impact touchdown.
So now I'll elaborate on how we incorporated the NASA Goddard technology made available to us. The product that we incorporated was the frequency diversity pulse pair algorithm. So what this algorithm basically does is that it sends out 2 short pulses in a very small time span, and these pulses then hit a moving object and they're received back by a Doppler radar. So by adding the system to MagGlyde, we add a Doppler radar to our system, and this helps us to get a better estimate of the position of the airplane, and it enhances our understanding of its whereabouts, making us our approach much more precise.
The possible challenges include magnetic influence upon the aircraft electronics. To prevent this, we can use a material which has very high magnetic permeability. And eddy currents, we have to study this about in more detail and characterize its impact. Hysteresis, we have to study this and we have to make use of this during switching the poles of the magnet.
Our major markets are civil airport authorities and militaries which can do away with arrestor wires and catapults on their aircraft carriers.
So now let's come to the cost. We will, the cost is divided into phases. So as you can see here, in the first phase, we will develop miniature prototypes of the pad units and a fully functioning MagGlyde system in closed laboratory conditions. And then we will move on to the second phase, in which the mini MagGlyde will meet virtual nature, that is a simulated environment. Then in the third phase, we will develop a final large-scale prototype of MagGlyde. These are our potential funding sources, government
20
R&D grants,
seconds.
etc. So as you can see. So thank you for your time, and now we are open to your questions.
Thank you so much. There is a system called ILS, Instrument Landing System, which is being used for decades to help aircraft land and take off, right? How is this system better or innovative than ILS?
The ILS is used in civil airport authority, in civil aviation, and it works it is not actually magnetic, but it allows the aircraft to come into a corridor, a virtual corridor kind of thing before landing. And one of its types is called CAT-3B, if I'm not wrong. And it still has a threshold that it cannot work beyond, it cannot work beyond a limit, like if the visibility is less than 70 meters or something, so CAT-3B is, the system fails. And our system is foolproof. It can work in virtually zero visibility.
And I would like to add on to that by saying that our system is entirely automated. So as we've listed before, that the leading cause of accidents is improper estimation by the pilot, and that happens when not when the plane is like traveling, but when it comes into the final approach. And that's the part that we're trying to automate here, to just reduce landing and save lives.
Well, thank you so much.
Spoke about automation. What is also interesting is a lot of accidents in the past have also happened because of automation, you know, when the pilots put the plane in autopilot mode. How do you see that technology failure will not impact, have an actual impact on, say, some kind of accidental damage? Say a technology failure could possibly impact, or the question is, how do you really foolproof the technology to ensure that you don't have accidental damage because of technology malfunctioning at some point in time?
We can use AI and ML, machine learning, in this algorithm. And what's more, that since we are using AI and ML, we can have 2 or 3 parallel processing units. So all the results will be cross-checked, and we can have a nice 100% accuracy.
And and another thing I would like to add on to that is that I don't know if anyone here is familiar with data deduplication. So what we're going to basically do is something that makes our system very unique. We're going to store all the approaches. Like I said, the way that we divide the pad units is most important because it decides which part of the airplane will come up and which part of the airplane needs to be stabilized the most. So we will store that, and whenever there is a plane with a similar approach, the set of protocols can come into action, and it can decrease the response time. So obviously the room for error also is minimalized.
Sure, thank you.
I'm not sure if I missed it, but what is your plan for testing this product?
Okay, so I said it during the cost time. We'll divide the process of research in 3 phases. The first phase, we'll develop a mini prototype in a closed condition where the temperature and pressure can be maintained so as to just to regulate the magnetic field. So in that, when the test is complete and we are successful, we'll move on to the second phase in which we'll test the same system, the miniature model, in an open area. So the temperature and that can be in an open area where we can actually control the certain conditions, but not all. So as we can control the conditions, we'll test it in real life. So it will react, and then when we will develop it further by research, etc. So we can test it. We need time for that, and we have the second phase is completely full of that. The third phase, after we are successful in the second phase, we move on to the third, which will be a large prototype of the same conditions and all. And after the third phase is almost the final, which will go to the final product, which will be sold to the aviation industry.
Let me add on to this. In one of the stages, we can use UAVs or drones for testing. And we can gradually scale up from small models to large actual size models. So any lessons learned from that stage will help us in our final stage.
I saw on your diagram, you showed it on the runway. What space is like 1,000 feet by 100 feet, or how much space do you need on the runway? And actually, how big is each panel that's on the ground?
Okay, so that panel that you're talking about is approximately on the runway. We've thought about it approximately being a 5-meter squared hexagon. And the arrangement, it's spread across the normal runway length, and in military aircraft carriers, the runway length is usually 300 feet, and we can shorten it down to approximately 200 or 150 feet.
Okay, and do you have any idea about obstacles as far as the weight management, like repeat abuse of takeoffs and landings of very heavy aircraft? Will your prototype be able to support that? Because it's very thick, stenciled concrete to land those.
Yes, we're currently researching on the material science, yes. And that's why we have chosen a honeycomb shape, a hexagon shape, because that's the naturally most viable and the perfect shape and most perfect, yes.